welcome back. So yesterday we discussed in the previous lecture about drainage pattern, and by now you must have must got the clear idea about that, what is the difference between the drainage pattern and channel pattern. So let's quickly look at different drainage patterns, which of course we have briefly discussed. So most commonly seen drainage pattern across in most of the regions, you will see that you have dendritic pattern, you have trellis pattern, and you have parallel drainage and all that. And in most of the regions you will also see the radial pattern. So these are one of the few most common commonly seen drainage patterns on the Earth's surface. So dendritic pattern develops above homogeneous geology. Trellis pattern developed over tilted or flooded strata. Radial pattern develops over domes or volcanoes. So we also saw some examples of radial drainage and dendritic pattern. Also I was showing some examples from Himalaya, where the sub-Himalaya are showing very dense drainage network. So drainage pattern, trellis, if you take, is irregular tree-like features you will be able to see, and they will be flowing in many directions. Of course, they will meet the smaller streams which are generated or developed and in the source area will join, but they are in many directions. Common in massive rocks or flat-lying stratas, and such drainage is developed due to strong resistance of rock. Headward development of valley is negligible, so it will keep on developing at the same place. Then we have parallel drainage. So parallel or subparallel drainage formed on sloping surface, common in terrain with homogeneous rock, and development of parallel rills, gullies or narrow channels, commonly seen on gently sloping surface. Now this gently sloping surface could be a natural surface or due to tectonic deformation. So this example I was showing from Pinjore Dune or close to Chandigarh, where the satellite photo on which I was showing you the parallel drainage. Now coming to the radial drainage, what you see is the center portion. You don't have any development of any drainage, but the streams are flowing in all direction. And again, similar example I have shown from higher Himalayas as well as in the foothill zones, which we discussed in the previous one. So mainly the stream radiates out from the center, so it is a topographic high. So central part will be higher, and so either it is in volcanic cone or domal areas, or even warped area because of the tectonic deformation, which will result into the formation of radial drainage. Rectangular drainages are commonly seen due to presence of joints and fractures. So if you are having the fractures and jointed regions or the areas in where you have massive rocks or foliations in metamorphic rock, then you will tend to see the formation, because they are what we can also say that they are, this type of drainage are structurally controlled drainage. So the fractures and joints are formed because of weathering also, but most of the the places it will be related to the ongoing deformation. So such fractures can control the flow of the drainage, because the streams or the water in the stream will try to flow and take the least resistance path. Hence, if they find the channel, the way through which the water can flow easily, and those are the fractures or joints, then they will start flowing and try to develop a rectangular drainage. Then trellis drainage are again rectangular drainage arrangement, where you will see, and the main stream is this one, whereas the tributaries mostly are been seen that they will join at almost at right angle to the main stream. So they are formed in the region where the main stream are parallel and very long. This pattern is common in area where the edges of the folded sedimentary rock. So it flows across the folded sedimentary rocks, and sedimentary rocks usually are been seen in combination of weak and resistance rocks and form a very long belt. Annular drainage, stream flows almost circular in fashion or in concentric path along the belt of weak rocks in an area which is marked by domes or basins. So very much somewhat similar to radial drainage, but this will give an impression of a concentric path or the pattern, or almost a circular pattern. So again, this figure, if you remember, so you have trellis pattern, tree like, it will have the density of the drainage will be higher, density here is less, a rectangular drainage, and trellis pattern is what we see is that the main stream is flowing across the resistance rock or the ridges, folded ridges, and this terrain is mainly the sedimentary terrain, and then in the less resistance rock in the valley area, what we have is basically the parallel drainages which are joining the main stream. And then we have the radial drainage, which has been seen in the volcanic region or in the areas which are warped or we see dome. So in central portion is the higher area, and then it flows away from, all streams flows away from the center. Now quantifying stream network, mainly the stream order in a basin can be ranked using one or several schemes. So there are several schemes which are available, which helps us in identification is not a difficult part, but yes, ordering one has to be careful, because that will help us in getting the bifurcation ratio between the higher order stream, or we can say the lower order stream and the next higher order stream. So these are the two most commonly adopted ordering methodology given by Strahler and Shreve. Now the difference is not much, but if you see here that initial, like the first order, the smaller order streams which are at the source area or in the uplands where the river originate or the drainage starts, okay, in the headwater area, then two lower order stream meet, then it will result into the or the next order will be the higher order, that is second order, and then even the second order remains, because if this becomes high, the next stream where it goes and joined will become higher order only when there is an next higher order than first, or two second order streams meet, then it will become third order. And if you see this here, then you will be able to understand. So two first order stream gives the second order stream, and two second order stream gives the third order stream, and two third order stream will have, like the further downstream will have the fourth order stream. So now the fifth order will come when two fourth order stream will meet. So even any lower order than than this order, if it meets, it doesn't change, the order doesn't change, the order remains the same. So finally what we can say, that you have the smaller sub basins. So the up to this point you can say that this basin, sub basin, is the third order stream, whereas this one from here, if you take this one, is the second order stream. And then final the trunk stream is a fourth order, so we can say that this is fourth order. So this is after Strahler. And after Shreve, what we see here is that two first order, very much similar to the Strahler, meet, result into the higher order, second order. And then even if the any one lower order meets, then it becomes the third order. But this will keep increasing the order exponentially. Like what you see final here is that even in this short distance, where the morphology of the channel doesn't change, the main channel remains the main channel, but because of the ordering pattern, this final order of this basin is 18th order, which is too high. So this is not commonly followed, and Strahler classification is mostly adopted. So what it does here is that, even if you see here, this is what you have, is that the two first order becomes second order, and then this becomes the fifth order and much higher, because you have fourth order here and all that. So the classification is very random here, and that is one of the reason why this has not been used actually. So considering the Strahler classification of stream ordering, if we look at, then we have the first order stream, we have second order, and first order and second order meeting, still it remains second order, but two second order, when it meets, it becomes third order, and so on. So two second order becomes third order, and two third order streams results into the fourth order. So if you count the streams, so what it has been marked here is that the final trunk stream, because this is the outlet here, and if this stream goes and meet like fourth order and the higher order stream meets here, then this stream will become higher order. But if we take only this area of the basin, drainage basin, then this becomes the fourth order basin, whereas the sub basins which have been marked by the dotted line, it shows that these are the second order basin, and this one is the third order basin, and even this is second order basin, this one is first order basin. So if you count the stream order, because this will require, this number is required for bifurcation ratio, to calculate the bifurcation ratio. So then you have the stream order and number of streams here. So you have one first order, you have 16 streams. So if you count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16 and so on. The second order is 5, third order is 2 and fourth order is 1. So fourth order is the final here. So ratio you will get between the first order, for example, and the second order and the next higher order streams. So bifurcation ratio, again if you take, it has been given by RB, where and RB is equal to NU by NU plus 1. NU is number of segments of given order. So these are the number of segments we have, as we were discussing in the previous slide. Then NU plus 1 is your number of segments of next higher order. So you have, for example, 10 first order, then next higher order is 3 here, something like that. Okay, and RB tends to be constant throughout the series. Now it forms the basis of Hutton's law. So one is the stellar, very much similar to that. We also call this as that it forms the basis for Hutton's law of stream numbers. Okay, and this has been given. So this is for bifurcation ratio. So ordering is very much similar to what we were talking about in the stellar. So here what you have is the 10 number of streams are of first order. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, and the second next higher order is 3, that is second order. So you can have the ratio is 3.33. This is the bifurcation ratio. So now this number is important because this will usually, the hydrologist uses this number for flood analysis mainly. So flood intensity is considered to be a drainage discharge along a channel, because whenever there is an overbank flow or the flow or discharge is higher, then the capacity of the channel to siphon it out, the water, the excess water, then there will be an overflow, and that overflow or overbank flows will suggest or clearly indicate that the stream or the channel is in flooding state. So the flood intensity is considered to be discharged along the channel over time. Flood intensity will be influenced by several parameters, and one is your rate of runoff, then the channel pattern and shape, the number of tributaries and distance downstream. So this is very important, where you will be able to figure it out that the runoff, then the channel pattern, drainage pattern and tributaries, this all will be controlled or will be affected by the subsurface geology and the geological structure. So this is very important, and well, if you understand this, then you will be able to talk about in better way about the flood hazard. So in stream order, the smallest tributary are designated at first order, that what we have seen, and those where the first order tributaries joins are second order, and so on. Then you have third order and all that. So lower order stream have short lag time. So this lag time is that one of the example we discussed of Uta river, that in Uta, that the lag is basically between the time of precipitation, that is the rain, and the flooding state. So the smaller streams will have very short lag time. So if you have more number of smaller streams or lower order streams, the flooding will be very fast. So what it says is that low order stream have short lag time between rainfall and flood. So this part is important because this will tell you whether the area will come into the flooding state faster or slower if there is an heavy rainfall. So lower order stream have short lag time between rainfall and flood and are more prone to flooding. Higher order stream with many tributaries are less prone to flooding, because higher order streams are wider and the pattern or the shape will be different than the lower order stream, and it will in terms of the length also it is comparatively longer. So it will take, even with the with many tributaries, they are less prone to floods. So this is another important point which you should remember. So drainage morphometry and its influence on the discharge. Now the drainage shape or basin shape is also plays an important role. So drainage network of river basin shape and channel pattern are most vital morphometrical factors that play significant role in increasing rate of flow through the drainage system. Even with higher bifurcation value, and this is the example which we are trying to show you for two basins where you have one is elongated basin and another is a rounded basin. So even if the RB values are higher in elongated basin, the hydrograph is very smooth, suggesting less discharge. And similarly, rounded basin with same basin area, so basin area of the rounded basin and the elongated basin is very much similar, or it is same, having a low RB bifurcation ratio shows high discharge. So this is what has been shown here. So you have the elongated basin and then you have the higher bifurcation ratio here, and then you have the rounded basin and the bifurcation ratio here is less. So the hydrograph, that is the discharge and time, which shows the time which has been taken to bring the channel, the main channel in flooding state, it is very smooth here. Now in the other case where the bifurcation ratio is low, that is the rounded basin with same basin area having a low bifurcation, but it shows very high discharge, and this can be seen based on the very sharp, because this hydrograph is very smooth and time taken is very different as compared to this one, but the discharge is high here even when the RB value is 3, whereas here the bifurcation ratio, so you have more number of streams here as compared to this one. So what is the reason for this? The reason is if you compare the distance, that is very important. So the length along which the drainage has been spreaded out, that is very important. The smooth curve of narrow shaped basin, so this one is the narrow shaped basin with high bifurcation ratio, can be explained by greater time lag or the water to reach the outlet. So the smoother curve over here and the narrow basin with higher bifurcation ratio can be explained by greater time lag. So the time lag which has been taken is greater as compared to what you see in the now rounded basin. So the greater time lag is there for the water to reach the outlet. So it takes time to travel through this longer distance, whereas the time taken from the upper, middle and lower reaches in rounded basin is comparatively less. So as soon as that, this is basically what we are looking at, is the shape of course is there, distance and the runoff. So the runoff time which has been taken by the water in the elongated basin is higher as compared to the rounded basin. So the water which is coming into the basin, the time taken from the upper, middle and lower reaches in the rounded basin is less, and that is the reason which causes higher discharge. So the discharge is much higher with RB value 3, and the discharge is much less as compared to in this case of the elongated. So basin shape and drainage density influences the discharge also. So stream order and flood crest, or the hydrograph, if you see, this is what we discussed. The first order streams have no tributaries but join to form a second order stream, and so on. This is what we discussed and which has been shown here. So what it says that the lower order stream tends to respond rapidly to storm or heavy rainfall with steep hydrograph. So it will get into the flooding state very fast, because water has to travel only a short distance, but in case of the higher order stream, it has to travel the longer distance. Now this is the reason that such streams provide less time for flood warning for downstream residents. So if you are having more number of lower order stream, then it is dangerous in terms of the flooding for the downstream residents, because they have smaller drainage basin and carry coarser and larger sediments for a given area. So this is the another disadvantage of having lot of higher order or lot of smaller order streams in the region, whereas the higher order streams with numerous tributaries have longer lag time between the storm or the rain and the downstream flood. Their hydrographs are less peaked and covers longer time period. So it gives enough time to issue the warning. So flood warning time for the downstream residents is longer. So we will stop here and we will continue in the next lecture, talk few more examples of flood. So this topic, I hope it helped you in understanding the morphology of the fluvial landscape and also its importance for understanding the flood hazard. Thank you so much.